we were talking about functions, relations, things like that. So we are in section 2.3, functions. And we mentioned something called a relation, which just looked like it was a set of ordered pairs. And I guess that's true, but it's not super interesting, really. But really all it is some kind of machine, some kind of system that pairs an input with an output. That's all that this process is. In fact, we're going to learn later on when we define functions like x squared minus 2x plus 1, it's the same idea. It's the exact same idea. So let's finally define a function. A function is a relation, and I think we did this last time, but I'll reiterate it. A function is a relation where for each distinct value of the first component, there is exactly one value for the second component. And that sounds awfully vague at the moment, and I agree with you. So let's actually work an example of this. Let's determine if each of the following are functions or just relations. All right, the first one. Let's see, what do I got here? So it's a set of ordered pairs. So let's see, let's go back to the definition of a function. Let's see, a function is a relation where for each distinct value of the first component, there's exactly one value for the second component. So the first components here are 1, -3, and 4. 1, -3, and 4. So each distinct value of the first component. So when x is 1, the first component is 1, you get just the value 2. There's only one thing that the number 1 maps to. When x is -3, you get 17. Same thing. When x is 4, you get 9. It maps to only one value. So just by the strict definition of being a function, this is a function. What we're really looking for is we're trying to make sure that you don't see two different instances of x values. You don't see the same x value showing up multiple times and trying to go to different y values. So if we have this point 1, 2. If we had another point in there like 1, 0 or 1, -30, and we had that in addition to this first one, that would be something that would fail for it to be a function. That's how it would screw it up. So this is a function by that definition. We can actually define some really interesting terms, domain and range. The domain is just the set of all possible x values that the relation or function defines. So it would be 1, -3, and 4. And it doesn't even have to be in order. So you've probably seen domain and range before. You've always heard, oh, domain is the set of all x values, range is the set of all possible y values, and for the most part, yeah, that seems to be a good way to define it. The range then is the possible y values 2, 17, and 9. Of course, we will more formally define domain and range a little later on. That's a solid definition for it. Okay, let's try another one. Let's see if we can make it A little bit different. Because I know just everybody here was just dying to see sets of points this morning. They said, "Oh, I can't wait for college algebra. We're gonna look at sets of points." Oh man, just exciting. And yes, you're right. You have every reason to be excited because this is just the most exciting thing on the planet. All right, let's look at this next one. Negative 4 comma 5 is the first point. So what it does is it maps the number x value negative 4 to a y value of 5. Again, that doesn't seem very profound, but what we're going to do is we're going to see later on what that really means, how powerful that actually can be. This one maps a negative 2 to a 1. This one maps a 0 to a 5. But this one maps a negative 4 to a negative 31. And it's like, whoa, hold on there, partner. You're trying to map negative 4, this x value, to two different y values. You're trying to map it to both 5 and negative 31. Now, it's still a relation. A relation is just a set of ordered pairs, I suppose. But that fails to be a function because for every different x value, you have to only map to a single y value. So negative 4, both they try to map to two different y values. That means this is not a function. You could still talk about the domain and range. You could still say the domain for this one. Just because it's not a function, it can still have a domain and range. I suppose. Negative 4, negative 2, 0, and then you don't need to put this other negative 4 here because you've already taken care of it as a possible x value. No repeats needed in a set. The range, I don't know, 5, 1. We already have a 5 there, so no need for it. And then negative 31. Bada bing, bada boom. That's just about the most interesting thing on the planet. Now, this is not a function, but does have this domain and range. We can, though, do something that will help us out a little bit. We can get rid of this point. Be gone, evil point. And now let's just make that our set. No problems for me there, Pilgrim. And now, the way it's written here, this actually would be a function. Each individual x value is only mapping to exactly one y value. But wait a minute, Josh, you say. Look, the y value of 5 is showing up in two different places, and there's two different x values that map to that. That's actually okay. In other words, it's okay to have a repeated y value that has two different x values going to it. But what you can't have is repeated x values that are trying to go to multiple different y values. Unfortunately, there's an analogy which is a bit grim that I could draw here concerning. Well, you know what? I won't draw it. Just will not. It's not bad or anything, but yeah, basically you can't have multiple x values or the same x value going to multiple y values, but you can have different x values go to the same y value. It's so weird and Raven, but it is how it is. This is a function now. And of course, the domain and range are simple. The range would only have two values, 1 and 5. Let's look at a couple other ways to visualize relations. You could use these little XY maps. So let's look at some more examples. Let's call this example C. And so here's the set of all x values, here's the set of y values. And what we can do with that is we can actually just use arrows to point to the relationships. The x value of 1 points to a y value of 2. So that would be the ordered pair 1, comma 2, if you were to write it out as ordered pairs. Negative 2, the x value of negative 2 maps to a y value of 4. And then let's say that the x value of 3 maps to a y value of 2. So this would be like the set containing the points 1, comma 2, negative 2, comma 4, 3, comma 2. What do you guys think? Would this be a function, yes or no? It would, yeah, it would be a function. Again, it's okay that you have multiple x values going to the same y value. What wouldn't be okay is if like this 1 was trying to point to 2 different values. If I tried to do this, and I'll even put it in a different color, if this was trying to go on, you say, I rebuke you, evil one. No, this evil one, literally in this case, this 1 is trying to point to 2 different y values. That's a problem. It's okay that multiple y values are being pointed to because there's different x values doing that. So, yes, function. All right, what if we played with it a little bit? Let's try another one. Let's call this D. I like to make sound effects. I'm sure you guys love to hear the sound effects. So let's see what's going on here, Pilgrim. Will. Negative 4 is pointing to 17. 15 is pointing to 5. 15 is also pointing to 17. And then negative 6 is all on its lonesome. What do you guys think? Would this be a function, yay or nay? Yes or no? Well, the negative 4 is okay, but 15 is a single x value pointing to multiple y values. That creates a problem. So no, this is not a function. The fact that negative 6 here does not get pointed to is actually okay. It's actually not a big deal. That's not causing it to fail. But no, not a function. Because a single x value is trying to go to multiple y values. What we're going to see is that eventually, we're going to talk about graphing functions, things like that. And we are going to see that it has to pass something called a vertical line test. And we're going to see it's just another expression of what we already know to be the definition of a function. We could even express these things as tables. A simple table of x, y coordinates. And so this is just the coordinates negative 3 comma 0, 14.5 comma negative 21, and pi, remember pi is just some number, 3.14 blah blah blah, pi comma 4. What do you guys think? Is this a function, yay or nay? Yeah, I hear some yays out there, and yay, you guys are right. Yes, function. Yep, that's a function because no single x value is trying to map to multiple y values. That's it. Well, wait a minute there, Pilgrim. What if I throw one extra point into there? It's really just not all that interesting. And you can immediately see this is a problem. Uh, nope, clearly that now fails to be a function because you're trying to map the same x value to multiple y values. But then what if I did that? What do y'all think? Is that a problem? This actually will still be a function because this is just a repeat. And it's just like we don't even need that information there. We already know that 14.5 maps to negative 21. This is a repeat. It can be deleted and there's no harm, no foul. So yeah, we can tell that that's not going to be a function, or that, excuse me, that this will be a function here. So we already kind of looked at domain and range. We even already kind of gave a basic definition for it. I kind of verbally stated it, and yeah, it's a good definition. It's the set of all values of the independent variable, which is usually x. The first component is the domain. So here you go, just to formalize it, write it out. The domain. Of course, the domain in general is actually going to be something that is a little bit more challenging than you'd think. It's going to be a little bit more challenging than you'd think. That's okay. And of course, the set of all values of the dependent variable, the one that is sensitive to the independent variable, which we usually use y to represent. It's called the range. Simple enough when we just write out a set of ordered pairs. The domain is just the set of all the x values. The range is just the set of all the y values. So that's not so bad. It's not so bad. But it does get a little bit more complicated whenever you start defining functions in a different way. Maybe if you start showing the graphs of functions, or heck, what if I had something just absolutely wild like this? Wait a minute, Wilbur. Wait just a second there, guy. You were just showing me all these relations. You're just writing out a bunch of ordered pairs, right? Like, oh, remember we had 1, 6, 2, 8, negative 3, 7. You just gave me a bunch of ordered pairs. This is not just a set of ordered pairs. This isn't just a bunch of points smothered together. Actually, it is. It is. All this does, all that something written like this, a simple equation, all it does is tell you pick an x value, and this will then tell you what y will come out of that. Pick any x value you want. Pick, so you can even make a table. Oh, that's a bad line. You can make a table, you can pick any x value you want. So hey, why not pick x equals 0? You plug a 0 into this, you'd get 0 here, then you'd just be left with the negative 7. So when you plug a 0 in for x, you get a negative 7 for y. Okay, plug in a 2. Plug in a 2, all right. You have to evaluate it now. Let's see, this will be 8 plus 8 again is 16 minus 7. So when x is 2, y is going to be 9. All this thing here does, it simply tells you the relationship between x and y. Earlier, when I was writing out sets of ordered pairs like this, I was doing the same thing. I was just telling you for the x values, the valid possible x values. Here's the y values that associate with them. It's the same thing here, only now the way it's written suggests that we can pick virtually any x value we want. And so now you see how the domain gets a little more complicated. How can I tell, just from looking at this, what x values I'm allowed to plug in, if you will, or what x values are in the domain? Well, that's a good question. We are actually going to find out this is called a second degree polynomial, and all polynomials have a domain of the real number line. So actually you can use any real value, real number you want for x. Y, on the other hand, the range is going to be a much more complicated procedure. So we won't quite handle it just at the moment. But yeah, all an equation is, this is just a set of ordered pairs. This thing right here in red is just a set of ordered pairs. It's nothing more than that. It looks worse than that, but it's not, I promise. It's just that it could be an infinite set. It could have an infinite number of ordered pairs because there's an infinite number of x values you could choose. So now suddenly the domain and range becomes a little bit more complicated. And so we do need to really understand kind of things like graphing, the kind of shapes that certain equations make when we graph them. So let's do this. Oops. Find the domain and range of, let's find the domain and range of a few of these things. But let's do it on graphs. So let's say you have a function. Let's use purple, a nice purple. And now let's say you're graphing a linear function. A linear function, which is a fancy way of saying a line. The arrows imply that it goes on forever and ever and ever in this direction, and forever and ever and ever in this direction. And we want to find the domain and range. Now, what are some of you automatically tempted to say the domain and range are? What are you guys thinking based on your previous experience with algebra?
All real numbers.
Yeah, all real numbers, is that what I heard? That's correct. Yeah, you're thinking it's all real numbers, and you're absolutely right. It's one of the few times where I don't just set you up and say, nope, no, you're absolutely right. It is all real numbers. But let's just talk real quick why, because this is your x-axis, it's your horizontal axis. And now, no matter where you go on the x-axis, you could find a point on the line that is basically attached with that. Right here you could, but even here, there's basically anything you want on the x-axis has something on the line. The same is true along the y-axis. You go up and down the y-axis, then you can find a point, even though it looks like it's not there. Remember, this arrow draws it on, so you can actually find something. So that's going to be a telltale sign that the domain is all real numbers. And in this particular case, it's not the rage. There's no machines to rage against here. The range is also all real numbers. Okay, we say, yay, dandy, that's just so fine. So much, therefore, that it blows my mind. But let's just talk about a couple other ways you can say all real numbers. You can use this symbol, so it would be all real numbers for both x and y, the domain and range. You can also use interval notation, negative infinity to positive infinity, something like that. Maybe I'll draw it a little bit better than that. Those are all different ways you can say all real numbers. And when I say real numbers, I mean not things involving I, the complex coefficient or the complex constant, whatever you want to call it. No, they got to be real numbers, no I business. So yeah, you can just look from the graph how that works. Along the x-axis, you're thinking domain. Along the y-axis, you're thinking range. Well, Now let's screw everything up. Let's try a different function. I'll use the same graph. Let me give myself a little more space, maybe. Now I'm going to have to draw this freehand. So I apologize in advance. Let's make a parabola. That's not so bad. That's not so bad, guys. Let's make a parabola. It looks like a smiling cat or something, or like the hamburger helper guy. Um, yeah, let's say that this is going to be parabola. Now remember, a parabola shaped like this is for the graph of a quadratic, of a second degree polynomial. Just a little thing to remind you. We're actually going to talk more closely about the shapes of, or the graphs of quadratics. But yeah, that's a true statement, surely it is. Now, one note, if you're trying to find the domain and range, you're going to need to know what this bottommost point is down here. The vertex, if you will, is the term we'll use for that. And so I'll tell you that that point, I'll provide you with that information. It's the point 2, -5. And then the arrows shoot off to infinity in both directions. And so now, remembering that the domain is the set of all possible or valid x points. The domain is something we're looking along the x-axis, and if you can go along the entire x-axis and always find something on the graph, on the picture of the graph, on the parabola, that is attached with that, you're fine. And knowing that these go off, now it looks tempting to say, won't the line buck up and go straight vertical? No, it actually never will. It never will. It looks like it could, but it actually doesn't. And what that means is that you can go anywhere on the x-axis and find something on the graph that find a y value that attaches with that x value. That's an awful fancy way of saying that the domain is, once again, all real numbers. The domain is going to be all real numbers. The range, however, will not be. Because notice the absolute smallest y value you can get if you're going up and down the y-axis. The smallest you can get is -5. There's no y value that dips below -5. So suddenly the range is no longer all real numbers. Not the case. The smallest it goes is 5. Now you can have 5. You can actually attain 5. So what we're going to do is we're going to use a bracket on the 5 for our interval notation. And then you can go all the way up to infinity. I'll just use 2 O's. And you always use a parentheses on one of the infinities. So this is saying it goes as low as 5 and can attain 5, and then it goes up to infinity, but we use a parentheses because you technically can't attain infinity as a possible value. Let's pause. Let's take a moment. Do you guys have any questions about this at the moment? Any questions on this? Is this, what's that?
Oh, they're saying it should be -5, not 5. I was trying to type it.
Oh, you're right. Oh, thank you very much. You are absolutely, see, you guys are ahead. That was a test, like, to see if, like, you're paying attention. No, you're absolutely right. Thank you, guys. Yep, the lowest you can get is the y value. So this 2 here doesn't actually matter. It's nice to know that, but it doesn't tell us anything about the domain. But the -5, you're right. That is the lowest y value you can attain. Thank you, guys. 5 points for Gryffindor, huh? All right. So that's from, I think that's from Star Trek or something like that. One of those franchises. I actually asked my class the other day. I asked one of my classes. I was trying to remember, You guys might know this. I still don't know it. What's that movie series where the main character is named Harry Potter, and he's got a lightning bolt scar, and he goes off to that school to learn about magic and stuff? Does anyone in there? Does anyone know what that series is called? Does anybody? The main character is Harry Potter. Well, I'll tell you what. I want you guys to think about it. I want you guys to think about it, maybe do a little research, and maybe next time we meet, let me know what that movie series is called. I think it's based on books as well. I was saying it was like Star Wars or something, but I have no idea. So go look that up for me. Of course, you can't tell that I'm smiling and clearly being sarcastic because you cannot see me, but that's just life. Let's actually determine the domain of some more things. And instead of graphs, let's graduate to a big boy, big girl school here. And let's just make it nasty. Not nasty, but let's make it something that requires a little bit of thought. A little bit more thought, I should say. Because sometimes looking at a graph, I hate to say it, that's almost easy. That's almost like, you just look at the graph, you can glean a lot of information from it. But suddenly, when you write, in this case, if you write functions in this manner, you're trying to figure out all x values and y values that are valid and will work. Of course, in this case, we're just going to look for the domain. The domain is all we want. Now, here's the trick. If I just give you a set of points, a set of ordered pairs, the domain is awful easy to get. So is the range. Just, okay, what are all the x values, what are all the y values? And it's because I've explicitly stated the points to you. The graph is even, it's a little harder than that, but it's still pretty easy to glean the domain and range off the graph. But suddenly when you write it like this, you have to think in 4 dimensions here. So the domain is the set of all valid x values. It's all possible x values that I am allowed to plug in here. Now, what they don't tell you is that we really only want real values. And that seems a little bit weird because, Josh, the very first section we studied in this course was complex numbers, things involving I, which were not real. If you have to bring I into the mix, you're not real anymore. So how come you gave us that tool and then said, nope, you have to ignore it? That's a great question. It's just because sometimes you have to know when to use it. Sometimes you have to know when to let it go. In this case, we are not wanting to deal with complex numbers because when we make a graph on the XY coordinate plane, which is really what we're trying to get to, when we make a graph on the XY coordinate plane, we're assuming the entire x-axis is real numbers and the entire y-axis is real numbers. You can actually graph things that involve the I, but it gets really nasty really quickly. You almost think of I as like another variable, and suddenly that requires you to go to a new axis. So you can talk about 3- and 4-dimensional graphs. In a 4-dimensional graph, you can't really actually graph that if you think about it. Not without showing change over time. So put another way, we only want real numbers. So normally, there's no restrictions on here if I could use complex numbers because even if the inside of a square root went negative, that's okay. We take the square root of a negative number and we get I out of that. But because we've brought I into the mix, it's no longer a real number. So in this case, we are restricting it. So the only thing we're worried about here is making sure the inside of the square root does not go negative, or else you got to bring I into the mix. That's the key here. That's going to be what helps us figure out our domain. In other words, the inside of the square root, this business right here, must stay greater than or equal to 0. In other words, 8x plus 3 has to stay greater than or equal to 0. And suddenly, we now have a system for figuring out the domain. The domain is related to x values. This is literally, in math terms, this is our way of saying, that 8x plus 3 has to be greater than or equal to 0. This means then we could solve for x. Move the 3 over, you get 8x greater than or equal to negative 3. Divide both sides by 8, you're going to get x greater than or equal to negative 3/8. Ta-da! You just found your domain. Now, you can, so basically, if you plug a negative 3/8 in here for x, you're going to get a 0 inside the square root, but that's fine. I can take the square root of 0. I just can't take the square root of a negative number in this case. If you put in any x value greater than negative 3/8, that's fine as well. If you put x equals 0 in here, 8 times 0 is 0, but then you're adding 3, you're going to just get square root of 3. And while that's an ugly number, it's still just a real number. If you put x equals positive 10 in here, you're going to get 8 times 10 is 80 plus 3. You're going to get square root of 83, which is fine. But wait a minute. You try to put any value that's less than negative 3/8 in there, maybe negative 5. 8 times negative 5 is negative 40. And even though you're adding 3 to that, it's going to stay negative. So then you're taking the square root of a negative, and that's a problem. So the domain is just, it's the set of all valid x values. It's the set of all x values that we're allowing ourselves, we're indulging ourselves, if you will. And so then the domain for this particular one can be written, if you want to use interval notation, that's usually going to be the case. So it can go as low as negative 3/8, and it can actually be negative 3/8. So we'll use a bracket, and then it can go on to infinity. Okay, so that's the domain. The range is a little bit harder to see. That's why we didn't exactly say, but I guess we can talk about the range real quick. The range is all possible y values. If you think about it, if you throw on your thinking cap, if you can never put negative values inside the square root, that means that the only things that can go in the square root are 0 and then positive things. You take the square root of 0 or positive things, you're going to stay in the positive realm, or you can get 0 itself. So in other words, put that the long way. The range, it turns out, because you're only sticking positive things or 0 in the square root, you can only get positive things or 0 out of it. So the range is actually going to be, with a bracket, 0 to infinity. That's a little less easy to see. It'll become a little clearer when we move on in this chapter and we see, oh, well, all we're doing is taking the parent function of a square root and we're shifting it and stretching it a little bit. We're shifting it horizontally, but that's going to be okay. So the range is 0 to infinity, and we kind of just reasoned our way through that. It gets messed up if I put a negative in front of the square root, because you can have a negative outside the square root, and that doesn't create a problem. It's only when there's a negative in there, and that's actually going to completely alter the range. So for the moment, take it maybe on faith. Take it on faith. Let's look at another one. In a quick note, the things that we're going to find, when you're talking about domain, you're talking about x values that can be plugged into a function that won't create any problems. Some of the classic problems in math we just looked at, one of them was trying to take the square root of a negative number. You know that's going to be an issue when it comes to graphing, so then you have to handle that. Another one of our classic problems in math that's going to affect domain is trying to divide by 0. Dividing by 0 is the devil's work. We won't allow it. We won't do it. So then you're also in the domain, you're going to have to ignore or throw out x values that would cause us to divide by 0. But we'll deal with that when we get into rational functions. Let's try one more. And let's determine the domain and range. Now, if you're following along so far and you're like, Josh, this is, this is pretty straightforward stuff. I agree. This is straightforward stuff, but I promise you, domain and range can get real ugly real quick. So all we're doing is introducing you to the idea of domain and range. And then in order to really jump in, sink our teeth into it, we are going to have to look at more complex things, at more complicated things, graphing, what do we do when we graph, moving, shifting things, stuff like that. Okay, so here we have y equals negative 2x plus 5. So let's think. I mentioned the two major problems in math that can plague our domain, that can cause issues with the domain. Trying to take the square root of a negative number, or trying to divide by 0. Do either of those problems seem like they're going to come up here? What do you guys think? Doesn't that look pretty straightforward? Negative 2x plus 5? Yeah, I think it does. Yeah. That doesn't look like there's any problem. Can you think of an x value that can't be plugged in here? Well, pick any real number you want. You can multiply it by negative 2, sure. You can then add 5 to that, sure. So just from pure simple reasoning, it looks like there's not going to be any x value that causes a problem, which is a fancy way of saying that the domain is going to be what, guys? All real numbers. Yep, I agree. Negative infinity to positive infinity. And yeah, that's absolutely right. You may secretly, backhandedly know that this creates in the xy coordinate plane a line with a slope of negative 2 and a y-intercept of 0, 5. And you're absolutely right. And you know that a line is going to, as long as it has non-zero finite slope, a line is going to be okay. The range. Now, here's what I'm going to say. Don't just say the range is all real numbers, because the domain was also all real numbers. Remember, if you're talking about a parabola, that's not the case. So the range here, that one's actually a little bit harder to deduce unless you do know a thing or two about the graph. Again, this is going to be a line with, I don't know why I lined down, with slope of negative 2, the number in front of x, and with y-intercept, remember it's a coordinate, don't just say 5, that's the lazy way. It's a coordinate with an x value of 0 and a y value of 5. So I'll whip up a very simple graph of that. I won't even get Uber specific with it or Lyft specific or any of the other rideshare apps. Let's see. It would cross the y-axis at 5, but it has negative slope. So it would look something like this. So now you can immediately see why the domain is all real numbers. You can also see why the range will also be all real numbers in this very, very specific context. It's because you can pick anything on the y-axis and there's something partnered with it on the red line. But wait a minute, Josh. You said we want to try and reason through these without using the graphs. Yeah, that's half true. You know, it's a little give and take. Now in the next section, in section 2.4, we're going to have a nice review over lines, linear functions, y equals mx plus b form, what all of that means. You might be a master at it. You might be humbled a little bit. by what I have to show you on that. But it does help to kind of think about the graph. Some interesting thoughts. Not everything that's a line will automatically have a domain and range that's the real numbers. Basically, any linear function which graphs as a line will have a domain and range of all real numbers if you have a non-zero finite slope. If your slope is 0, you got a problem there, Pilgrim. You're going to make a horizontal line, and the range is actually going to be just a single value. It's not going to be the real numbers. You also have to have finite slope. Josh, can you have infinite slope? Yeah, infinite sloping line would be a vertical line. So we're going to talk about that a little bit more. I'll go into more detail about those weird kinds of lines. But here, our slope was -2, which is not 0, and it's obviously a finite number. So then our domain and range is all real numbers automatically. So that's fun. That's fun. Let's talk about function notation. And this can actually get kind of complicated. We usually let y be f of x. So as a quick side note, this is read, the way I read this is literally f of x. It is not f times x. I'm not saying take something f and multiply by x. No. What that is saying is that y, so let's say you had this simple one. Let's say y is equal to, I don't know, let's make it a quadratic. How about -4x squared plus 17? That's quadratic. It's missing an x term, but that's okay. It's still quadratic. This might be something, and what it does is it tells you x and y pairs. Now what they say is that y and f of x are interchangeable. And I'm like, we're almost splitting hairs over semantics, over definitions of things. That's kind of true, but it's better just to say that by writing it as f of x, you are explicitly stating that y is a function of x, meaning x can do anything it wants in its domain, and y then is sensitive to that, is dependent on that, according to this formula. So to say y and f of x are interchangeable, it's almost confusing. That's why they sometimes just say let y equal f of x. But that's not really, I don't like that. I don't like that. That's just a little much. But what we're going to say is that this is a function of x, this f thing. Well, you can also have other function definitions. G of x equals -3x plus 6. You can have h of x. Usually you won't see I of x because I is a special, constant. It's the complex constant. But you can do that, and so suddenly now you can see how the notation gets ugly, because now we could call this thing just f, and this one is the g function, and that's also accurate. So what the heck's going on? Well, we're kind of just playing around with how we define things, and it is confusing, I'll give you that. Here's the real reason we write f of x. It's because I want to have a quick system of saying like this, f of 3. What that means is plug a 3 in for x. And so, in this case, it would just be -4 times 3 squared plus 17. I want to have a quick system of being able to plug in x values and get y values out of that. If I had written it like this, y equals -4x squared plus 17, then in order to find the y value when x is equal to 3, you have to literally state something ridiculous like evaluate y whenever x is 3, or something ridiculous like that. Find the value of y when x is equal to 3. And that's just a mouthful, and when you're trying to work a lot of problems here, It's just too much. But if I just say f of 3, it's immediately obvious what I mean by that. It means plug a 3 in for x. So really, function notation is just a more convenient way of expressing this same idea. So they say y and f of x are interchangeable. You can, fine, that's fine, I'll concede that. Whatever. It is definitely more convenient to write it like that. A quick note, if we're saying that y is a function of x, then that word function is coming up. That means it's a function. That means when I graph it, there is no one x value trying to go to multiple y values. That is not going to be an issue here. In fact, now that we have graduated and we're talking a bit about graphs, I can preview. There's something called the vertical line test. And what that says is if you take the graph of something and can run a vertical line across the entire graph and never hit the graph more than once, you have a function. That the vertical line test means you can run your eye across a graph real quick and decide if it's going to be a function. And so now this is bringing everything full circle to how we started the class. Today, we started the class by asking, is this a function? Is this not? But now that we've gone on to graphing things, we can definitively say it pretty quick. So let's look at a few examples of the vertical line test. You've probably dealt with it before. Let's look at a circle. Whatever this center is, whatever this radius is, I'm not even going to label it. Do you guys think that this would pass the vertical line test? Well, let's find out. Let's take our vertical line. We're going to run it across the entire graph. Setting off alarms. No, that fails the vertical line test. You have to be able to run the vertical line entirely across the function, and it never touches the function more than once. But anywhere you move it, it's just a circle. Anywhere you move it, it's automatically going to be touching the graph twice. Anywhere you move the vertical line, it's going to touch the graph more than once. So no, a circle is not a function if you keep the whole circle. That's why the equation of a circle could not be written as y equals something. Remember, the equation of a circle had to be written like this. Because you can't just isolate the y like that. Now you think you can, but you'll end up having to take the square root of both sides, and that's going to lose some information when you do that. So that's exactly why we can't, that's why we didn't write the equation of a circle as just y equals something. We had to write it like this. It's because a circle is actually not a function. So when you write an equation as just y by itself over here and then a bunch of x things over here, you're explicitly, it's automatic that you're talking about a function. Let's look at another quick example. So the vertical line test says you can run the vertical line across the entirety of the graphed relation and never have an issue. So how about something as simple as a line? A line with non-zero finite slope, which is usually what you'll see, but we need to say it. What do you guys think? Will this thing here pass the vertical line test? Yeah, I think it will. Let's make ourselves a vertical line. Now remember, these arrowheads aren't actually on the graph. They're just a little visual wink and a nod that tells you, hey, this line goes on forever. But in theory, in reality, the arrowheads aren't actually, the arrowheads aren't actually there. They're just telling you this line keeps going and going. So now, if I run the vertical line across, ooh, that's smooth. That's real smooth. And, maybe that will make it a little more vertical looking. There we go. That's a little better. Ooh, that's smooth. The vertical line can completely go across and only ever touches the graph once. It only ever touches the blue thing one time everywhere across the entire domain. Remember, the black vertical and horizontal lines, those aren't actually the graph. Those are just something that allows us to label and see what's going on. Those aren't actually on the graph. Yeah, this thing passes the vertical line test. It never touches more than once. So this passes, not phases, it passes the vertical line test, which means it's a function. But I could have told you that because I already knew I could write a line as just a y equals equation. Y equals mx plus b. Ugh, okay, let's rewrite that. I already could have told you that. So it's actually pretty powerful, this idea that you can write something as just y equals. You're automatically implying that it's a function as long as you don't try to do anything funky with the x's, which we're not. We'll revisit the vertical line test a little later on in the semester. So yeah, f of x, not f times x. Keep that in mind. So let's use function notation to simplify these following things. Let's find f of 2 for f of x equals 3x minus 5. Bless you. Was that a sneeze or a cough? Sneeze or a cough. I couldn't tell mine. Because here's the thing. I have always been a strong advocate, very, very passionate about saying, how come you can bless a sneeze, but you're not supposed to bless a cough? I think you can bless a cough. I think there's nothing wrong. If someone coughs, you say bless you. I got no problem with that personally, especially if it's just a rare cough. If they just have a cough and they're coughing constantly, you can't. It's just not practical to constantly be blessing that person. You only have so many blessings you can give out in a day. Anywho, so yeah, I've considered just putting considerable amount of money, resources, and time into political lobbying for that. So that's how serious I am. So I use weird words here, use function notation to simplify. Okay, well, all I'm really saying is plug a 2 into that. And it is pretty simple. 6 minus 5, it becomes. So you get a 1 out of that. In other words, f of 2 equals 1. In other words, when I plug a 2 in for x, the function spits out a 1 for y. In other words, that means the coordinate, the ordered pair 2 comma 1, is a coordinate that would be found on the graph of f of x equals 3x minus 5. If I were to go graph that, the point 2 comma 1 would be on the picture of the graph, the line. That's actually kind of cool. So what you don't realize you're doing that, but you are. Because at the end of the day, all a graph is of a function. When you graph it, you go put it on there, all you're doing is drawing every possible xy coordinate pair that works. That every x value and then its corresponding y value that it spits out for that. That's actually a great way to think about graphing. Okay, let's do another one. Let's make it fun, because I know you guys like to have fun here. How about we find f of 1/2 for the function f of x equals negative x squared plus 5x minus 2. Well, you're sitting in the classroom, you might have your notes out available to you in front of you, writing stuff. Try it out. F of 1/2 means I plug a 1/2 in for x. And when I plug things in, I usually like to put it in parentheses. Try that out. Do it on paper. It's fractions. Fractions are less fun, but you know, you got to deal with them. The order of operations says you got to do the squaring first, then you apply the negative to it. So follow along with me. 1/2 squared is to take 1/2 times itself, which will give you 1/4. Another way to think about that is an exponent on a fraction, you have to raise the top and bottom to that exponent. 1 squared is just 1, 2 squared is just 4. Then you can do something like that. And then it's fractions, so you'll need a common denominator. That common denominator is clearly going to be 4. Negative 1/4 plus 10 over 4, so negative 1 plus 10 is 9, but then we subtract 8, so it just comes out to 1/4. Real fractions heads know. So that means the function evaluated at an x value of 1/2 spits out a y value of 1/4. And furthermore, that means that the coordinate 1/2, 1/4 would be on the graph of this function. And yeah, it's a fraction, but that's okay. Where did you get 8/4 from? Because what I need to do, this was a 2. This was the whole number, 2/1, if you will. And so in order to get that to have a denominator of 4, that's how it would convert. You'd have to multiply the top and bottom by 4. So that would make this 8 on top over 4. Does that make sense? Makes sense. Thank you, Gracie. Very good, very good. Makes sense. Candles make sense as well. And I'll let you unwrap that one in your mind. That was dumb. That was a dumb joke on my part. I apologize. Finally, let's even do one more. Let's do one more, and let's make it even more interesting. Let's up the ante. Let's say that you're now talking about a function g instead of f. That's okay. We're not going to worry about it. But now instead of plugging just a number into it, we're going to plug in a completely different algebraic expression. Ooh, oh, ooh. Everyone go, ooh. This is going to be called function composition. We're going to see it a little bit later on in this chapter, so not today. And what it says is that earlier, remember if you had like f of 2, you were plugging a 2 in everywhere you saw x. Well, let that be your guiding principle here. Now we're going to plug an x plus 2 everywhere we see an x. We're going to do substitution. So this means that g of x plus 2 is going to be -3. And now instead of just putting x, we're going to put x plus 2. And again, it's a good habit to go ahead and anytime you're plugging something in for x, put it in parentheses. That's a good habit to get into. Because then that suggests that this -3 distributes which is exactly right. Negative 3 times negative 2 times positive 2 becomes negative 6. And so this is a little bit funky. Negative 6 plus 5 is negative 1. That's a little funky. Some of you may not like that. But in math, as in life, sometimes you just have to deal with things that you don't like. Some of the things I don't like. The other day I was on a toll road and I was confused about which lane to take because it was not a city that I live in. And so I drove through the right lane and I didn't have enough cash to pay the toll. And I said, is this 1996? Can I use a credit card or do you have to only take cash? And they say, we only take cash. So here's what we're going to do. They gave me a little thing. It was like an insufficient funds notice for a toll of $3.25. And they said, take this slip of paper and mail us a check or money order for the exact amount. You have 10 days to do so, or we're going to issue you a ticket. And I said, can I just pay that with credit card? And they said, no, you have to send us a check or a money order. You have to mail it to us for $3.25. Which, you know, I'm a busy man. I got a busy life. I have a dog. He's a bloodhound, and I was taking him to the vet yesterday. Maybe if you guys are really good, I'll show you guys my dog sometime. I'll bring him on camera. He's sleeping right now. I was busy yesterday. I had to go to the bank. I had to go get a money order for $3 to. Yeah, why? Why? That was like an hour of my life for a $3 toll. It was ridiculous. So here's the rule. There are things in life I don't like. Having to not be able to use my credit card drives me absolutely bonkers. Drives me bonkers. How many of you guys would want to see my dog?
Yes.
All right. I'll tell you what. I'll save that as a special treat for a little bit later. If I go wake him right now, he's going to be real cranky. So I'll say that as a special treat. Special treat. Keep in the back of your mind. And he's a full breed bloodhound. He's got giant floopy ears, and his name is Shepherd. The dog's name is Shepherd. Shepherd. He's named after a character, the main character of a video game trilogy that I'm a huge fan of. I think it's Harry Potter, right? Isn't the main character of the Harry Potter series named Shepherd? Right, the main character's got the lightning bolt scar. Anyways, this is weird jokes. Never mind. No, it's based off the main character of video games called the Mass Effect trilogy, science fiction stuff. So yeah, and he's a good boy. He's a very good boy. He's very sweet. He will sit with you, hang out with you. He doesn't bark a lot. He doesn't bork a lot. So he's a good boy. Okay, so maybe you'll see Shepherd next time. Finally, let's do one more. I'm going to whip up a graph for you. It's going to be the graph of a parabola. Let's not use green. Let's use black. All right, so I'm going to whip up the graph of a parabola. It's going to be a frowning parabola. It's upside down. It's going to look a little bit funky. Now, we're not so curious about the domain and range in this. Instead, what I'm going to do is I'm going to draw 2 points on the graph. I'm going to label them. So on this graph, here is the point. You know what? Let's just use their little dot thing. Here we go. That's much better. Let's say that this is the point negative 5 comma 4. No, negative 5 comma 2. How about that? And let's say that this is over here, the point, you do that. There we go. That's much better than me just trying to draw it by hand. Let's say that this is the point 4, comma, negative 2. And so this is the graph of a function. I won't define the function. I'll just call it f of x. But I won't tell you what it is, like x squared minus 2x plus 4, something like that. But we know it would just be a quadratic function. So here's what I'm going to do. I want you guys to help me. We're going to find f of negative 5. That one's going to be easy. Let's also answer this question. For what value of x is f of x equal to negative 2? That one shouldn't be a whole lot more difficult, but we only have 4 minutes left in class. This one can be done in about a minute, and then there's not enough time to really start a new concept, so I'm just going to kind of stall and buy time here and go very slowly. F of negative 5, what that means is plug a negative 5 in for x. What y value does that spit out, guys? Everyone shout, well, shout it, with a reasonable shout. Everyone shout it out. 2 is correct. I heard you guys. Very good, yes. And that's literally all it means. But all that does is drive home the whole point of graphing. All graphing is an expression. It's a picture of all the possible XY coordinate pairs, all the points that could work. So I know from looking at this graph that if you have an x value of negative 5, the only possible y value that can spit out is 2. It can't spit out more than that. Again, it passes the vertical line test. You can tell, again, the arrowheads don't count. It passes the vertical line test. So no matter what, f of negative 5 could not have been 2 as well as 7, 3. No, because it's a function. What we're going to see is that's actually a really important definition we're going to make. Now, this next one is actually going to be trickier than it looks. It's trickier than it looks. For what value of x is f of x equal to negative 2? In other words, what x value do I need to plug into the function for the function to spit out a negative 2? What do you guys think? 4 is right. Is it totally right? It's not. I tricked you. I just didn't label another point over here because notice that this has a y value of negative 2, but this thing over here would as well, the thing that is directly horizontally across from it. Ooh, gotcha. And so I didn't label that point, but it was a gotcha moment. For what value of x? There's actually more than one. So let's just say this happened to be, negative 7 comma negative 2 as well. So both x equals 4 and x equals negative 7. That's the trick. But that's okay, it's still a function. Because what that's saying is there's a single y value that has multiple x values mapping to it. That's okay. I just can't have a single x value going to multiple y values. And so while this thing would pass a vertical line test, it would not pass something called a horizontal line test. And that's okay, it's still a function, but if it also passed a horizontal line test, it has a couple of extra really nice properties. Specifically, it would be called onto as well, or no, excuse me, it would be called one-to-one. And we'll investigate that in more detail next time. 9 o'clock. Thank you guys so much. Y'all have a wonderful day. Yeah.
No, for them. Sorry.
Oh, sorry.
Set up a Google Classroom.